Now, the last thing which I'm going to discuss is another data structure, which is called a trie. Okay, trie, the name comes from information retrievals. Okay, so this is, and it's actually, if you do it proper, you read it like a tree. But since it gets a lot of confusion when you call this tree, people spell it like trie. Okay, so how do we do this? What is a trie and how do we use this? I'm going to give you an introduction, and in your sixth homework, you are going to build a trie. So a trie is, first of all, it's not a binary tree. Okay, so it might have more than 2 children, descendants. And that means you need to somehow keep these children in another structure. Only variables would not suffice. So, and the number of children might change. It's not fixed to something. So you need to be aware of that. And what it does actually is it holds a bunch of strings, character by character, in such a way that whenever you point to a leaf in the trie, for instance, in here, this is a leaf, the rest of the paths, first of all, the path from root to the leaf gives you the word itself. So if I'm talking about the word, then that would be W-O-R-D. Okay, so let me draw it once more because this is not very good looking. Okay, so W-O-R-D. When you select a leaf, the root, the path from root to the leaf, character by character, gives you a word for this example word. The cool thing is, the path, if you exclude the leaf, the path so far is the prefix of another word. So I might put K in here. So when I go from here to the K, it is going to give me the word work. So I can easily add something more to here so that it would give me the word warm. Okay, so the good thing is all of those have the same prefixes. So I can put K in here, so that might give me the word walk. Okay, so basically this is a trie. Okay. Let me continue from my slides. All right, this is an example trie. So if you look at this one, this contains the words. You go from the root. The root might be empty. And, well, there are a couple of ways to do that. But most of the time you do it like the root is empty. And then you start the words of each character from the descendant. Or you might do it like hold multiple tries. So you start the root from a single word, a single character, but you hold a number of trees in order to represent your words. So another tree for each beginning character. So if you do this, if you have multiple trees, then it's called a forest. Okay. But you can do it like this as well. So the root is always empty, and the first descendant is the first letter. And by the way, there are also other approaches. So you might not keep, so this looks like I keep the letters in the nodes, but you can also do it like keep the letters in the links. So if you can somehow affiliate the links with the characters, then you can do that way as well. But it depends on you, however you'd like it. So if you look at this one, now let's see which words are there. So we start with B. Bear is in here. Bell is in here. Bit, bull, buy, sell, stuck, and stop is in here. Okay, it's cool. Now, how do we use it? Well, it might change from it might change from case to case, but this is a special case. This is an example case. So what we have is we have a large string, which do have some words in it, separated by spaces, and there are some also punctuation marks as well. And what we do is we go over this string and index by index, I add the characters, and in the leaf, I keep the beginning. I'm sorry. Yeah, I keep the beginning index of the word as an additional information. So if you look at this, for instance, there is the word here in here, and we keep 69, which means the 69th character is beginning the here word. So if you look at this, there is also bill. Is this bill? Bit. I'm sorry, there is something wrong in here. This should be D. Bit. Because there's no word like bill. Okay, it should be double L's, or yeah, this is D. Okay, if you look at this bit, it has got two indexes. So it's 47 in here and 58 in here. Okay, so what did I do? So if I want to search for some words and directly move on to it, and now I got a now I get a structure which is ON, with the N being the length of the word. Okay, so the length of the longest word is your worst case search time, and it will give you the indexes, the places where this word is occurring. Cool, right? Now what you can do is you can also hold something which is called a compressed try. In the compressed try, what you do is basically you get rid of the unnecessary chains like those. Okay, so you see there is nothing in between, so you get rid of them. So what you do is you get this try, and you see this AR chain is not useful, so I put it as AR in here. And also this double L is not useful, I put it like this. This ID is not useful. This double L again, and there is nothing to reduce here. And this ELL can be reduced to that. The CK can be here. And also there is a chain in here, you see, that's interesting. So this can be reduced to TO. So it doesn't restrict it with leaves. There might be chains within the inner nodes as well. So you do it like this. And if you do this, this becomes your compressed try. But of course, it has got its own unnecessary hardnesses as well. Of course, this would be this would contain the depth of the compressed tree would be less, but also you have the burden. If you want to add a word, then you might need to split that node. Okay, so if for instance you want to add a stick, something like this, to the tree, okay, imagine you want to add the word stick, then you cannot add I to here. Okay, so then you need to, either you might do it like you start S, you put another T in here, and you continue like I and C and K. But the point is, if you do like this, then you got an ambiguous node structure, which is not very good. So the more proper way is to erase this altogether, or not erase, but reorganize it altogether. So it would go like T and O and P. And this will be like, actually, let me do it like this. OP, and this would be like ICK. And also there's the stuck. So yeah, I forget about it. So it's better to do like O, CK, and OP. Okay, so that would be the correct modification when you want to add the stack to it. So you see, you need to split this. And you need to handle the situation like this. And also now, yeah, this is what you need to do. Okay, this is called a compressed try. And you can even more shrink that, like you can store, instead of the characters themselves, you can store the beginning in this and all the information about the length of the try. So what you do is, for instance, if you want to put the C inside it, you start from the index of the letter instead of the letter itself. So you start from the 1. I'm sorry, I think this is, you start from 0 and you get 1 letter. And then the next is you start from 1. I think that one is the index. You take 1 letter and you put the letters like this. You represent the letters like this, and you get a full tree based on integers instead of strings or characters. Oh, this is one way to handle that. But I believe there is not much of a need to do that. These would suffice. There is also something which is called as suffix trees. I think this was called the suffix tree. Suffix try, I'm sorry. So what does those do? Now these handle the situation from the reverse point of view. And what you say is you put the descendants from the decreasing order, by the decreasing order. So what you do is, for instance, you got a word minimize, and you start to add as a children the post ambles. So E, you put it like here, and then if you go from Z, what you can do, you put it in here. So E is already there. So now let's look at the last 3 letters, I, Z, A. So you can directly put like a thing like I, Z, E, but as you go towards this side, it will be updated. Let's see how it's going to happen. So there is also M, I, Z, E. So you add one more thing. M, I, Z, E. And you go on and you get another I. So there is I, M, I, Z, E, and there's I, Z, E. So why keep both of those? Now I delete it. I put an I descendant, this guy over there, and I put as ZE and MIZE. And then I continue, nimize. So I put it like this in here. And there is another E, inimize. So you, mize and ZE is already there, so you put nimize. All right. And there's also minimize. So what you can do is you, you also already have mice in here. So mi in the beginning. That's a little bit hard to see. So you join those together. into mi prefix, and then you can end up with minimize, and or you can end up with mice. So how that might be useful? Well, actually, now you can make search inside the word. Okay, so in the previous try structures, you can only search for the whole words, not the part of it. You need to search inside the try in order to find the part of it, which is not very useful. But if you look at this one, again, in logarithmic time, you can search for the part of the word in here. Okay, so if you are searching for mice, then it takes you only 2 steps to find out that it's inside the word. This is called the suffix try. So